All right, it is officially 11:30. The recording is live. I know some people just came in, but we do have a in-class problem set for today. I'll hand that out for those who just came in, I'll hand out your copy when we get closer to it. 1 week from today, we have our next exam, module exam 3. That, of course, means that this week is our last set of topics for that exam. Today's topic, gases, is primarily a calculation-heavy topic, so I hope we brought our calculators. And then on Thursday's lecture, we will go into a new topic called drawing. So on Thursday and Friday's concomitant workshop, we will be focused on a new topic called drawing. So you'll need your pencils, and if you want to crayons and all that stuff, that's fine, but pencils are sufficient. Last week, we spent a lot of time on acidity and basicity, just kind of going over the basic concepts of acids and bases as well as their calculations. We also spent a little time talking about the concept of titration, which is an experiment you'll be probably doing this semester in lab. As a reminder from lab, we're rounding the curve on our wet lab experiments. I don't know if you guys have taken a look at the schedule yet, but for the next 3 to 4 weeks, we don't have wet labs. We have nothing but dry labs. Over the next few weeks, we're getting into what I consider the most difficult set of topics for Chem 300. So we'll be spending a lot of our lab time focused on practice. Do we have any questions before I begin lecture? Yes. So the next exam is on Tuesday. I would probably say use that exam as like now you should start working on it, because it'll be approximately a month and a half after the next exam from the last day of classes. I would probably say a month. Yeah. So after the next exam is absolutely a good time that you need to actively start working on the presentation, meeting with your group mates, communicating and all that nice stuff. Of course, there are some topics that we won't cover until like a week or so before the presentations. So for some of you, you might need to start reading ahead. But for the most part, once we finish module exam 3, you can start working on the presentations. Any other questions? Okay, I know a lot of us just came in. We do have an in-class problem set for today. When we get to that section of today's class, I'll give you your copy. Let's talk about gases. Okay. So in our discussion of gases, or starting our discussion of gases, it's important to remember that up until this moment, we haven't exactly studied or investigated gases specifically. I mean, sure, way back when in module 1, we talked about gas particles. In reactions, we talked about gas evolution. But our discussion of gases has been very limited. And one of the biggest reasons for that is one of the simplest questions of gases is, how do we know gases are real? You see, on one hand, when it's a gas, for example, like Febreze, we can clearly see the particles spread upon spraying the Febreze can, and eventually it disappears to the naked eye. We know the gas particles are there, but we can't quite see them. Some gases have a smell associated with them. For example, on your stove, if you've left the gas on, traditionally you're able to smell that leakage. In some other cases, for example, mustard gas, some gases have a visual element that, of course, allows you to prove, yes, the gas is real. I can see it right in front of me. I understand that it exists. But for the most part, almost every other gas is naked to the invisible eye. I mean, we know that we breathe in and out oxygen and carbon dioxide, even if we don't exactly see it. We know that the atmosphere has other gases, such as nitrogen, even if we can't see it. So how do we know gases are real? Well, let's think back to our different states of matter. When we think about solids, we know solids are real because we can weigh them. And when we weigh them, we traditionally get them in grams, kilograms, pounds, or otherwise. But the fact of the matter is, when it comes to solids, we can see solids, we can weigh solids, we're able to quantify how much of a solid is present. In the case of liquids, we measure their volume. Our standard units here are, of course, liters or milliliters. You might sometimes have fluid ounces, et cetera, et cetera. Liquids, you can pour it into a cup, you can pour it into a bottle, you can pour it into a beaker, measuring cylinder, whatever, and we're able to measure the exact volume. In the same way, for gases, the physical quantity that we're able to measure is pressure, which has an SI unit of ATM, which stands for atmospheres. Now, let's spend a moment and recall one of the earliest things we talked about with gases, which is, of course, their particles and their motion. Way back when, we talked about how gas particles are spread apart, very far away from one another, and they're continuously moving. In other words, gas particles are very mobile. As a result, if they're trapped within a container, what ends up happening is frequent collisions. Now, just like cars on a highway, these collisions don't just occur between particles. Yes, of course, one particle can collide into another, but sometimes these particles will collide with the wall itself. These collisions are measured in terms of pressure, where pressure is defined as the amount of force divided by the area. So how do we know gases are real? Well, we know that the molecules, the particles will collide not only with themselves, but with the wall. And we're able to measure the pressure of these collisions. In doing so, we're able to quantify the amount of gas present. How exactly do we do this? Well, we measure gases, or rather the pressure of gases, via a barometer. You've probably seen it if you've ever watched a weather report. And the thing about pressure is that it has varied units. I've already told you that ATM, aka atmospheres, is the SI unit for pressure, just like liters for volume, just like grams for solids. But you might also see other types of units, not just in this course, but in your textbook or online resources. One such example is millimeters mercury, mmHg. If you've ever gotten your blood pressure taken, you might recognize this unit. This is traditionally what the doctors or nurses measure when they say your blood pressure. I think the ideal average is like 120/75 or something. It's millimeters mercury. You might also see a term called torr, T-O-R-R. This is most commonly found in heavy science circles. I would say a physicist would most likely use torr. Car owners are familiar with PSI, pound per square inch. If you've ever filled up the tires of your car, you know that each tire traditionally has an ideal amount of air in it, measured in PSI. I think most cars are around 30 to 32. And the last one you might see is PA, which is pascals. These units all represent the pressure, which is a quantitative measure of those collisions. ATM will be the one we most commonly see in this class, use in this class, but you do see others in general. So it becomes very useful to know what the conversions are. 1 atmosphere is equal to 760 millimeters mercury. 1 atmosphere is also equal to 760 torr. 1 atmosphere is equal to 14.69 psi. And 1 atmosphere is equal to 101,000 pascals. What you might see online is 101 kilopascals, where K means kilo, something we've seen with grams, liters, kilograms, of course. Yes.
So these are all the same temperature. There's just different types of measurements.
Correct. Just as how with solids, we have grams, we have kilograms. Just as with liquids, we have liters, milliliters, ounces, fluid ounces. These are all varied measurements or units of mass volume that we are accustomed to. Just like with pressure, the SI unit, the standard unit is ATM. You might also see these varied other forms, but they're all measurements of pressure. Our discussion of gases leads us to our next topic, which is known as the ideal gas law. The ideal gas law, an equation, is given as PV equal nRT. A lot of scientists just affectionately refer to this as PivNert. Just a shorthand way of referring to it, PV equal nRT or PivNert. Now, some of these variables should already be recognizable to you. P, of course, is pressure. And when using the ideal gas law, pressure must be in ATM. Then we have volume, V, which we know, of course, is in liters. N is the number of moles, whose unit is simply MOL, aka mole. R is our new variable. We've never seen R before. This is what's known as the universal gas constant. And it has a constant value, a set value of 0.0821, where the units are liters atmosphere all over mole Kelvin. So new term, new value, universal gas constant, 0.0821 liters atmosphere mole over Kelvin. By looking at the universal gas constant, we recognize some of the units. Liters, of course, is for referring to volume. Atmosphere, referring to pressure. And mole, referring to mole. The only one left that's unexplained is this K right here. As we go through the list, the only one left is T as in temperature. That letter K may be recognizable to some of you. That's the unit of temperature that we'll be using, aka Kelvin. We once talked about Kelvin very, very early on in the semester, way back when we were talking about units and measurements. Kelvin represents another unit of temperature that we will use when dealing with these calculations. The conversion, to be specific, Celsius to Kelvin, in other words, to go from Celsius to Kelvin, you simply add the temperature to 273.15. To go back, aka from Kelvin to Celsius, you simply subtract 273.15. Now, this particular conversion is one that is incredibly unique. Every other conversion we've seen in this class, kilograms, grams, liters, milliliters, moles, mass, etc., are all some variation of multiplication or division. In the case of Celsius to Kelvin and vice versa, you're just adding or subtracting a value. So it isn't anything to multiply or divide. You simply add or subtract 273.15. The key thing I want you to know here is that when dealing with gas laws, you always have to convert to Kelvin. Always. As of right now, the reason why is not abundantly clear, but once we start doing some questions, you'll understand exactly why that is. Now, the ideal gas law represents one of the most fundamental equations that's used to understand gases. And from the ideal gas law, we're able to derive various forms of it. So our next topic is derivations of PV-NRT, PV equal nRT. Now, bear with me here. If I wrote the equation PV equal nRT, and I remember that R is our gas constant, what we can do is we can divide both sides by NT. In doing so, we cancel out the moles and temperature on the right, such that our overall equation is simply PV divided by NT is equal to R. Don't forget that that R value is a constant, 0.0821 liters atmosphere all over mole Kelvin. Now, the beauty of recognizing this expression is understanding that, well, if this entire thing is a constant, then we can make very easy predictions about gases. For example, if we were to measure some quantity of a gas, let's say at 9:02 in the morning, some initial reading. The time, the specific time isn't too important. I'm just making clear at some random time, if we measure a pressure, volume, or temperature, we're able to say that P1V1 all over N1T1 is equal to R, where 1 refers to the initial readings, the first set of readings. If we were to wait a couple hours, let's say we were to come back at 4:05 p.m. and take a final set of readings, we can come up with a very similar equation. P2V2 all over N2T2, where yet again, this entire expression is equal to R, the gas constant. What this allows us to do is make a very simple expression that says P1V1 all over N1T1 is equal to P2V2 all over N2T2. This expression comes from the idea that both of these, P, the 2's and the 1's, are equal to the same value, the same constant, so they can be equated to one another. This is known as the combined gas law. So two primary laws or equations surround gases in general. We have the ideal gas law and then the combined gas law. Now, I'd like to point something out, something specific to Chem 300. Oops. For the purposes of Chem 300, N will be a constant. For the purposes of Chem 300, N will be a constant. What this allows us to do is cancel out N1 and N2, since they'd be identical, such that the equation we will be using is simply P1 V1 all over T1 is equal to P2 V2 all over T2. Understanding the use of these two equations, the combined gas law and the ideal gas law, is paramount to success in this topic.
Thank you.
Where if we take a second to look at them, we can understand their use cases. In other words, when we would use one over the other. The ideal and the combined gas law. The ideal is PV equal nRT. And the combined gas law is P1V1 all over T1 is equal to P2V2 all over T2. When do we use whichever one? Okay. In the case of the ideal gas law, we use the ideal gas law when we are studying a gas at a single moment. No initial, no final, just here is a gas, here is some information, calculate. In contrast, we use the combined gas law when studying a gas at different time points. AKA, there is a very clear initial set of readings and a very clear final set of readings. Now, you may be wondering, it's clear on the left-hand side, the ideal. Okay, that's very clearly, you measure the temperature, you measure the volume, you can calculate all that stuff. It's at a specific single moment. How do we use the combined gas law to do that? Let's talk a little bit about the utility of the combined gas law. Starting from the general equation, P1V1 over T1 is equal to P2V2 over T2. As of right now, this equation, this expression, this law, whatever you want to call it, doesn't give us our very nice and easy A is equal to B times C or D or whatever. There isn't a very clear, this is what we're calculating. It's just an expression. But say, for example, from the combined gas law, we wanted to calculate P1 and P1 alone. We can manipulate this equation to get to that P1. Let's talk about how that works. We have P1 over here on the left. To get P1 alone, we need to get rid of V1 and T1. What we're going to do is we're going to multiply the left-hand side by T1 over V1. Where does that come from? V1 is on top. By multiplying it by a fraction, they cancel each other out. Same thing for T1. T1's on the bottom. When it's multiplied by the top, it cancels out. If that's still not visually clear, write it out like this. When we write it out this way, at least a little bit more visually cohesive, we're able to very clearly see, okay, yeah, I can see how these two pieces cancel each other out. And remember, whatever you do to one side, you have to do to the other side. From there, we're able to say that P1 is equal to P2 V2 all over T2 multiplied by T1 over V1. Notice those subscript labels, the ones and the twos. Remember, we talked about how the ones are our initial set of readings, and our two is our final set of readings. Based on this logic, these two will not automatically cancel each other out because they're meant to be two completely different values. Whoops. We can further simplify this expression by writing P1 is equal to P2 V2 T1 all over T2 V1. And herein lies the difficulty with this chapter. You need to be able to manipulate this equation, this expression, to get any value that I'm asking for. If I ask you to calculate T2, then you need to be able to manipulate this equation to get something that says T2 equal. I see a hand, Serenity. I can't hear you. So the difficulty of this particular topic, or rather this expression, is manipulating the equation. In fact, I actually once had a student work with a tutor and specifically develop each possibility. In other words, he worked with a tutor to get 6 different equations, and guess what he did? He memorized each of them because he wasn't confident on doing it during the exam. In general, I don't really recommend this, because then now you're memorizing 6 brand new equations. What I recommend you do on your own time is manipulate the equation a couple times, get some practice. But if you happen to have a perfect memory or otherwise, I'm not going to stop you from memorizing. The gas law also gives us some very cool information. For this next bit, we are going to draw 4 graphs in total. Okay. 4 graphs. I'll give you guys a second just to draw up the axes. It's an X and Y axes. As of right now, you don't know the labels. But we're drawing 4 graphs. Now, the combined gas law represented one of the biggest advancements in understanding gases. Because someone had the bright idea to say, well, what if we were to look at 2 specific variables? In other words, take, for example, this first equation up here on top. What if we were to say the temperature is constant? If we were to say temperature is constant, that means T1 and T2 are identical. That means they can be erased. The result of this is what allows us to draw a graph measuring pressure against volume. This graph looks like this. It is a curved graph that has an overall negative slope. The implication of this graph tells us that as pressure increases, volume decreases. Similarly, As pressure decreases, volume increases. Let's take a look at that. As pressure decreases, we see volume getting larger. This relationship was devised by a man named Boyle. Now, Boyle set off a trend. Boyle was like, well, I'm just picking one thing to be constant, temperature. Another scientist by the names of Charles had another bright idea. He said, from the equation P1V1 over T1 equal P2V2 over T2, Charles simply said, pressure is constant. If we're able to say pressure is constant, then we can erase the P values, left with V1 over T1 equal V2 over T2. When we plot this graph, volume over temperature, we get an overall positive slope. We can keep going. If we assume volume is constant, then we get P1 over T1 is equal to P2 over T2. This is the case where V is constant. If we measure the graph, if we graph this out, pressure versus temperature, yet again, we get that vertical slope. And in theory, that should make sense. They both have very similar looking expressions. They're a fraction. In the case of Charles, the graph tells us as volume increases, so does temperature. If volume decreases, so does temperature. Same thing over here. As pressure increases, so does volume. I'm sorry, so does temperature. As pressure decreases, so does temperature. This one over here was made by a duo, Gay-Lussac. The last graph that we will encounter is by a very familiar name, Avogadro. You all remember him way back in the moles chapter. We talked about Avogadro's number, moles. Avogadro had the bright idea to make everything else constant except for volume and moles. Now remember, I already told you that for the purposes of Chem 300, N will be a constant. So it will always be deleted. But that's not true in real life. N doesn't necessarily have to be constant, which is where Avogadro got his idea from. Very volume and moles. To no one's surprise, he again got a vertical, positive slope overall. Where we're mapping volume against the number of moles. Where, as we've already seen twice now, as one value increases, so does the other. In other words, as volume increases, so does moles. As volume decreases, so does moles. It may not seem like it, but these four graphs actually represent almost 2 decades of research into gases. You see, way back when, it was not considered an easy assumption to make one thing constant. But understanding these graphs allow us to better predict gases' behaviors. We're now going to move on to our in-class problem set. Please raise your hands if you don't have a copy. Anyone else? Okay. One for each of you. All right. Welcome to our next in-class problem set. Let me just bring up the document myself on my end. This is gases. Yes, the gas laws. Okay, I just need to format it. So let me just grab this one over here. This is 2025. This is Sumnus. Here it is. Gas laws. Whoops, I don't want to share the link. Nope. Good notes. Okay. Just now realizing that my calendar about pest control visiting my house is blocking the transcripts. Dealing with some black widows. That time of year, of course. And someone who has a couple animals, especially 2 cats who love insects. Definitely need to get that sorted. Okay. This is 2 pages long, front and back. I will tell you what your extra credit is for this worksheet at the end of today's session. But I'd like to go through some questions in particular. On the first page, we are going to go over question 3, question 5, and let's do question 1. So the first couple odd numbered questions. I'm going to move it over to another page so I have space. Starting with number 1. All right. 2 big equations, the ideal and the combined gas law. Being able to identify which equation to use is one of the most fundamental aspects of this topic. Let's read the question and try to understand which law we will be using and why. Whoops. The question reads, 22.5 liters of nitrogen is compressed from a pressure of 748 to 725 millimeters mercury. We're asked specifically, calculate the final volume. So in this case, the wording should be pretty clear. I have outright asked you calculate the final volume, meaning this is 2 time points. There is an initial set of readings, there is a final set of readings. If that wasn't clear, look at the rest of the sentence. It says compressed from. So it starts at 748 and it ends at 725. So everything about this question tells us we're actually going to be using the combined gas law, P1V1 all over T1 is equal to P2V2 all over T2. Let's take a second to identify what values we've been given, what value we're being asked for. From the wording of the question, we're being asked to find the final volume. So we're being asked to find V2. Based on that logic, we know that V1 must be 22.5 liters. Why? Because that's the only other volume mentioned. It says that much is compressed. We're told that the pressure started out at 748. So we know that P1 is 748 millimeters mercury. Based on that, we know that P2 is 725 millimeters mercury. This part is one of the very common mistakes people make. In other words, incorrect assignments. If you had this the other way, P1 is 725 and P2 is 748, you would in fact go wrong no matter what. So we have pressure and volume. The only thing not mentioned here is temperature. The fact that temperature is not mentioned is what tells us temperature is constant. So we can erase it. How do we know temperature is constant? Because it's not mentioned at all. Nothing about it tells us temperature has changed. We're allowed to assume temperature is constant. We have 3 of the variables, and we're trying to find V2. At this point, it just becomes plugging in and chugging. There are 2 approaches. You can plug, then rearrange, or you can rearrange, then plug. Both will lead you to the same answer, the same correct answer. It's just a matter of which method you're more comfortable with. Let's start with the left-hand side first. We're going to plug in our values, then we're going to rearrange. We know our values already. They're written up. We know P1 is 748. We know V1 is 22.5. We know P2 is 725. And we're trying to find V2. We can start putting this into our calculator. I hate this new stage manager feature. How do I, okay, let me come back. Oh, there it is, okay. On the left side first, 748 multiplied by 22.5. We see our value of, looks like 16,830. To get V2 alone, we divide both sides by 725. So here we've already plugged in. We're just rearranging now. We're dividing both sides by 725. We put this into our calculator. We're able to say 16,830 divided by 725 is approximately equal to 23.21. Which brave soul wants to tell us what the units of this value is? Yeah, liters. How do we know it's liters? Because it was told to us the initial volume was already in liters. That's where you plug in first, then you rearrange. Is that Paul? Yeah, what's up? Very good question. Very, very good question. Paul has pointed out or recognized that the pressure I gave you is millimeters mercury. Do you have to convert it? The simple answer is no. Why? Because if we plug this in, if we looked at the units, millimeters mercury times liters is equal to millimeters mercury times V2. Eventually, when we divide both sides by millimeters mercury, they cancel each other out. That's what tells us our volume is in liters. So that's a very good question. As long as the units are the same, you do not have to convert them. I've given you the pressure in millimeters mercury in both cases, so no conversion necessary. If I gave you, for example, one of them in atmospheres, then you would have to convert them. As long as they're the same, it doesn't matter what you convert. Now let's try to rearrange then plug in. P1V1 is equal to P2V2. To get V2 alone, we divide both sides by P2. This ends up V2 is equal to P1V1 all over P2. If we plug all our values in, we already know them. P1 is 748. V1 is 22.5. And P2 is 725. If we plug them all into our calculator, fraction, 748 times 22.5 all over 725, we get the exact same number, 23.21. Yet again, in liters. So both approaches lead you to the exact same answer. Our more math-inclined students will recognize that they are identical in terms of the actual math. Pick whichever one you're more comfortable with. But I promise you, you will be rearranging. Do we have any questions on number 1? Okay. Let's now do number 3. The question simply says, calculate the pressure required to compress 196 liters of air at 1 atmosphere to a final volume of 26 liters. So there's that word final. That word alone, final, tells us we will be using the combined gas law, P1V1 all over T1 is equal to P2V2 all over T2. Take stock of what we know and what we don't know. We know that the final volume is 26 liters. Therefore, we know the initial volume is 196 liters. Question is right now, what is P2 and P1? And again, this is where it gets tricky. It didn't say calculate the final. It didn't say calculate the initial. It just said calculate the pressure. So let's read the question to try to understand what's what. If we keep reading, it says 196 liters at 1 atmosphere. The way that's read is what tells us when volume is 196, pressure is 1 atmosphere. So we know what P1 is. What we're trying to do is find P2. Recognize pretty quickly that temperature is not mentioned. So we're allowed to assume it's constant, hence erased. We're trying to find P2. To get P2, again, we just divide both sides by V2. This is what tells us P2 is equal to P1 V1 all over V2. If we plug in these values, P1 is 1 atmosphere. I'm now purposefully writing out the units. V1 is 196 liters. And V2 is 26 liters. We can put this in our calculator. 1 times 1, 1 times 196 divided by 26 looks like that's equal to 7.54. And the question of units will always come up. But now by writing out the units explicitly, we should clearly see that the liters will cancel each other out, leaving atmospheres, ATM. And that's it for number 3. Do we have any questions on number 3? Okay. Let's now do number 5. The question reads, a weather balloon is filled to 150 liters. I'm sorry, a weather balloon filled to 150 liters at 10 degrees cools to -8 degrees Celsius. The question asks us to find the final volume. So we know what equation we're going to use. It's going to be that combined gas law, P1, V1, all over T1 is equal to P2, V2, all over T2. Let's take stock of what we do and don't know. The question is asking us to find the final volume, V2. Based on that, we know V1 has to be 150 liters. We're told that the temperature, T2, is -8 degrees Celsius. How do we know it's the second one? Because it says cools to. That's a final temperature. T1 is 10 degrees Celsius. Nowhere in this is pressure mentioned, so we're allowed to assume pressure is constant, hence erased. And from here, we're trying to find V2. To get V2 alone, we multiply by T2. In doing so, we cancel out T2. And whatever you do to one side, you have to do to the other side as well. Therefore, V2 is equal to V1 over T1 times T2. We start plugging in our values. V1 is 150 liters. Again, purposefully putting the units so we can see what happens. The temperature is 10 degrees Celsius, T1. And T2, we're told, is -8 degrees Celsius. We put this into our calculator, 150 divided by 10. All of that multiplied by -8, we get the answer -120. We can see based on the units, the Celsius cancels each other out. We're left with -120 liters. But this should piss you off. Can volume be negative? No. So what mistake did I make? I should have converted to Kelvin. This is why the Kelvin is necessary. It is totally possible to have negative temperatures. You put a negative into this expression, all of a sudden something else like volume becomes negative, which doesn't make sense. Similarly, freezing point, 0 degrees. What if I put 0 degrees in there? Anything divided by 0 is syntax error. Anything multiplied by 0 is 0. So what did I make the mistake? I should have converted to Kelvin. So I'm going to need to restart this. Looking at T2, I'm going to add 273.15. Let's put this in our calculator. -8 added to 273.15. We have 265.15 Kelvin. Same thing for T1, 10 degrees. 10 added to 273.15 is 283.15 Kelvin. Now that we've converted it, we're going to put those values in. T1 is 283.15 Kelvin. T2 is 265.15 Kelvin. Now we're going to put this back into our calculator. 150 divided by 283.15 multiplied by 265.15. We get a much more reasonable number, 140.5. And just as before, we do see the temperature units cancel each other out. That's what tells us our final value is in liters. So going back to something I think Paul was had asked earlier, did we need to convert, I'll see your hand in a second, Alita. Did we need to convert the pressure to ATM? The answer is no, we did not need to convert it. As long as they're consistent, they'll cancel each other out. That applies to pressure and volume. But for temperature, you always have to convert to Kelvin. And it is precisely to avoid these issues. If you have a negative Celsius, you're going to have negative volume or pressure. Always have to convert temp to Kelvin. Oh, have to convert. Aletha, I saw your hand. What were you asking? Okay. Do we have any questions on number 5? Yeah. I multiplied both sides by T2. In doing so, I canceled out the T2s. And of course, as you just pointed out, whatever you do to one side, you do to the other. Okay. This is use of the combined gas law. It's asking you to evaluate or investigate a gas at 2 different time points, a clearly initial and a clearly final. Let's now use the ideal gas law, which is pretty much all of page 2. We are going to do number 11. Okay. Immediately, one of the things we notice is that I've given you an equation. That's one of the clearest differences between combined and the ideal law. The question reads, how many grams of chlorine are needed to produce 1.6 liters of nitrogen at 1.2 atmospheres and 23 degrees Celsius? Let's think about what this question's asking. We are being asked information about one chemical and given information about another chemical. What technique are we going to use to solve this? The road map. We will be connecting chlorine gas and N2 gas. Let's draw our roadmap. I'm just taking a second to draw it out. I'm not filling anything just yet. I'm just putting in our labels and all that nice stuff. After seeing a lot of you work, I understand that some of you started to come into your own as to how you draw this diagram. I love it. I've seen different people with different variations. Mass, moles, volume, mass, moles, volume. And then, of course, this is ratio. Okay. Is that a question, Ryla? Yeah. We will eventually do it. Whether that happens at the beginning or the middle doesn't quite matter, but we will eventually balance it. Okay. Let's fill in the information we know and the information we're trying to find. The question says how many grams of chlorine. Okay, so that's how I know that this box up here is what we're trying to find. What's the mass of chlorine? And we're specifically told that we're dealing with 1.6 liters of N2. The roadmap ahead is clear. Volume to moles, moles to mole ratio, moles to mass. So let's start filling in all the information we have to know. Well, we need to know the molar mass of chlorine. Take a second to do that. There are 2 chlorine atoms. So that's going to be 35.25 times 2. That's approximately 71 grams. So we know the molar mass is 71 grams. Looks like we do need to know the ratio. So as Ryla pointed out, we will balance. It doesn't matter if you balance at the very beginning or in the middle. Looking at the given equation to balance this, what we're going to do is we're going to put a 2 in front of the NH3, a 3 in front of the Cl2, and a 6 in front of the HCl. The ratio between Cl2 and N2, we can see that is a 3-to-1 ratio. According to the roadmap, we need one more thing. Remember, it was volume to moles, mole ratio, moles to mass. We have our bus pass here and here. But what about molarity? Nowhere in this question did I give you molarity. I didn't give you those square brackets. I didn't give you that capital M. Molarity is specific to liquids or aqueous species. We are dealing with N2, a gas. So we cannot use molarity. So we need to add a new piece to the roadmap. To get moles of gas, we are going to use Pivnert, where the volume is 1.6 liters, but the bus pass we will be using is not molarity, it's Pivnert. So if we erase all the other bits and pieces, the roadmap becomes clear. Volume to moles using Pivnert, mole ratio, moles to mass. This topic represents an addition to the roadmap, stoichiometry. I mentioned when we started this topic, we're never going to be done with the roadmap. In fact, as we finish this course, we're going to continue adding things to it. Now we're adding gases. We see the roadmap. Let's go ahead and write it out. Whoops. Step 1, step 2, step 3. Let's go one at a time. Let me just make this a little bit smaller so I can keep the question in tow. Oh, I actually took the screenshot too. That's weird. Just grab that. Yeah, that's better. Okay. First step is going from volume to moles, specifically for N2. We will be using Pivnert. PV equal nRT. We are trying to find N, so we're going to actually divide both sides by RT. This is what tells us the number of moles is equal to pressure times volume all over R times T. Do we know the pressure? Yes. The question told us 1.2 atmospheres. Do we know the volume? Yes, that's in the roadmap, 1.6. Do we know the universal gas constant? Yeah, 0.0821. Do we know the temperature? Yeah. Question told us 23 degrees. Am I good to keep going? What do I need to do? Convert to Kelvin. Very good. So we need to convert the Celsius to Kelvin, which is adding 273.15. Just to make it clear, actually, I'm just going to put this in the bracket, 23 plus 273.15. We're now going to put this in our calculator. We have a fraction on top. We have 1.2 times 1.6. On the bottom, we have 0.0821 multiplied by 23 added to 273.15. Look at my calculator. Look at what values I've put in. Make sure you've put in yours as well correctly. Calculators can either be your best friend or your worst enemy in these types of topics. We plug this in. We get 0.079. And there's our moles. Now from here, it is our very standard approach, the roadmap we're used to. Step 2, which is going from moles of N to moles of Cl2, is a 3-to-1 ratio. That's a nice number, actually. 3-to-1 is the same as 6-to-2, which is the same as 9-to-3. In other words, we multiply by 3. When you multiply 0.079 by 3, we get 0.237. Now that we have the number of moles of chlorine, we can do our final step, which is moles to mass, specifically for chlorine, where we know mass is equal to the number of moles times molar mass, 0.237 multiplied by 71, 0.237, not divide, multiplied by 71 is equal to approximately 16.83 grams. And that's number 11. Use of the ideal gas law is in addition to our previously established roadmap. We are not introducing a brand new concept, but rather just adding on to our roadmap. Now, I'd like to point something out here vis-a-vis unit conversions. Now, we've already made clear you have to convert temperature to Kelvin. That avoids negatives, that avoids zeros. But what about everything else? Now, I told you when we did the combined gas law, as long as the units were consistent, they'd cancel each other out. But when using the ideal gas law, we have a gas constant, 0.0821 liters atmosphere all over mole Kelvin. You have to convert volume to liters. You have to convert pressure to atmospheres. So when using the combined gas law, as long as the units are consistent, doesn't matter. When using the ideal gas law, they have to be in a specific unit. And above all else, temperature must be in Kelvin. Do we have any questions of number 11? Yes, Alexia.
Point 237.
So we recognize from the ratio, this is a 3-to-1 ratio, right? Which is effectively times 3. So times 3. Your extra credit for this worksheet is any 2 questions from page 1. Any 2 questions from page 1. And any 3 questions from page 2. 5 in total. On Thursday's class, we're moving into our new topic called drawings. I'll also have already made your exam by then, so we'll talk a little bit about what the exam is going to look like. We're going to end lecture for today. If you have any questions, come talk to me after class. If not, see you guys on Thursday. Have a good day.